Yeah, it's my first time in BIOSPAIN. I'm Roger Burke. I'm the Chief Medical Officer at Horizon. It's not my first time in Seville since 2002. I've driven around Seville a few times to Cadiz and various things. I actually live in the Algarve, so Seville's my nearest big Spanish city. And the last time I was here, properly in Seville, was for the launch of galantamine, which is one of the licensed drugs for Alzheimer's disease. So it's probably fairly fitting to be back having launched one drug and here to talk about how we're going to launch another drug at some stage. So thank you for coming to this session. We have 3 speakers. I'm not going to do much talking. I've been told by the Chief Exec to keep it to a minimum. We've got Gina Swartz from Merck, who will give a sort of overview of things as they are now, and we've deliberately called it dementia maze rather than Alzheimer's maze because we don't want to concentrate just on Alzheimer's disease. We've got Clive Ballard from the University of Exeter, who's going to talk a bit about how we might utilise placebos in a more interesting way. And then Rajat, who's working with us on statistics, where we're looking at more complex designs, statistical designs for complex diseases, which is quite timely because the FDA have just brought out some guidance on that. Because we worry that, the language of Alzheimer's has been becoming the language of failure. People talk about we've failed for 15 years. Actually, we've learnt a lot, but now we've got to start applying it. And what I'm hoping from this session is we can disrupt the current thinking about how we collect and analyse data and start to think about how we might actually find solutions in the methods, methodologies, maybe even the hypothesis, in order to set up trials that will deliver outcomes that we've thought through and designed properly. So that's the aim of the session for you to leave with. Each speaker is going to speak for 10 to 15 minutes. We've got quite a good number, so I want to have a reasonable time at the end so that people can ask questions and get involved. So without further ado, I'll ask Gina to come up and do her first presentation.
Good morning, and thank you for inviting me to come up here and give some ideas and perspectives on potential ways to find a cure for dementia. And I will largely focus on Alzheimer's disease, but not exclusively. And I've been tasked with looking at what we can possibly learn from other disorders, and I've put neurodegenerative conditions in brackets because I'm also going to be alluding to non-degenerative conditions, diseases of the periphery, oncology, and think what we might be able to learn from these disease spectra. Just to say that these views reflect my own opinions and not those of Merck or MSD. So I think most of you, no doubt all of you, are familiar with the classical amyloid hypothesis, the cascade in which we have amyloid extracellularly and toxic intracellular tau aggregates, and we believe that these are the pathophysiological components that cause dementia in Alzheimer's disease. And as Roger has said, the last 10, 15, 20 years have seen a wealth of clinical studies in which we've developed symptomatic therapies and then sought very hard to define and develop drugs that will modify the disease progression. Unfortunately, thus far, we've not been successful in that task. And very recently at Merck, we've had to close our verabecestat or BACE inhibitor program in mild to moderate Alzheimer's dementia, as well as very recently we are shutting down our program in prodromal or MCI because unfortunately we've had to halt our studies because we've not been able to demonstrate any clinical effect. So the field, both in pharma and in academia, have looked beyond amyloid, and of course we're now starting to look at tau. We understand and know more recently that tau seems to be the initiator of the disease. Tau seeds peripherally and disseminates widely in the brain, and we now understand and believe that this is a prerequisite for which amyloid then seeds at a later date. So it obviously makes sense to start considering whether tau may be a relevant and beneficial therapeutic target in Alzheimer's dementia. When we look at drug development in AD as of last year, you can see from this quite busy slide that the vast majority of phase 3 programs are amyloid related, as indicated by the red stickers or markers. And coming up in phase 2 and even in phase 1, we also have several tau-focused based programs. Of course, our symptomatic department or area is not targeting to amyloid or tau and largely looks at other neurotransmitters and pathways. But you can also see that in our disease-modifying area, we still have a predominance of amyloid targets, but we are starting to see a wide host of other therapeutic targets coming to the fore. And if we break this down even further, you can see that in phase 3, more than 50% of agents look at amyloid. Does this work? I don't know if the point works. So you can see anti-amyloid aggregators, BACE inhibitors, immunotherapy, a small sliver targeting tau, and then we have some other drugs in development. Whereas in phase 2, the slice of the pie looks much more variable. We still have a large number of amyloid targets, anti-amyloid immunotherapy, anti-aggregators, BACE inhibitors, a greater proportion of tau targets, but we also have a lot of other mechanisms, neuroprotection, anti-inflammatory, antiviral, neurotransmitter, and neuroprotectants. So you can see that the field is starting to look further and to delve more deeply into other areas that may impinge upon the disease pathway. And I think part of the issue is that perhaps we still, even today in 2018, don't fully understand the complexity and the interplay of factors that converge together to cause Alzheimer's disease and indeed other dementias. So you'll again be very familiar with the classic deposition of amyloid and abnormal tau phosphorylation. We've been focusing on amyloid. We're now looking at tau. We're starting to look much more at the anti-inflammatory component. But the big question, and I ask this to you today, and hopefully we can discuss this towards the end of today's presentation, is the amyloid hypothesis dead? Do we put amyloid to bed and concentrate on other targets? Or do we still look at amyloid as a viable target and think about other means, other ways, other strategies to actually impinge upon this aggregating protein that we think we understand? Many of us in the drug development space have always thought of a linear progression of events leading to dementia, but it is clear that the complexity of the disease far outweighs that, and this multi-causal pathogenesis is much more likely to be the process. And this slide from Bart de Stroop, I think, illustrates quite nicely this very complex interplay of pathways interacting with the abnormal proteins in poorly defined and probably incompletely understood ways at present. And again, that leads me to this very busy slide. Don't look at the detail, just to show you that these are multiple different complex causatory hypotheses that may play a role. And to target one rather than the other, or to target a multiplicity of them, remains the challenge at play today. So let's step back and look at other disorders. I'm looking at neuroinflammation in the context of dementia. And I think we can step back and look at diseases in the CNS space, for example, like multiple sclerosis, where in the last 10 to 15 years, we have made huge advances in terms of targeting and relatively well treating at least the inflammatory component of the disease. Can we not apply the same approach in Alzheimer's disease? And I believe that we should be able to do so, not just in AD, but in dementia across the board. We need to better understand the innate immune response. We know that microglial and astroglial cells are activated, and we also have evidence from GWAS and other genetic studies that implicate several genes and several inflammatory pathways in sporadic Alzheimer's disease. We also understand that external factors, obesity, systemic inflammation, interfere with immunological brain processes and thereby promote disease progression. And finally, we hope to modulate these immune mechanisms and ideally lead to the development of new therapies for dementia. Microglial activation is a concept that we're beginning to understand much more in the context of CNS disorders. We know that we have a brain insult, whether it's trauma, ischemia, beta amyloid accumulation, or any other insult, targeting the microglia and astrocytes, which then results in them becoming activated or reactive and producing a whole host of pro-inflammatory mediators, cytokines, reactive oxygen species, nitrous oxide, etc. These then result in a breakdown of the blood-brain barrier. You have intracellular, you have transmigration of inflammatory mediators, and you have a whole inflammatory cascade set up within the CNS that then goes on and contributes to the neuronal loss and ultimate neurodegeneration that we see. So over the years, people have been thinking about this and have used COX-2 inhibitors, non-steroidals, which have largely showed negative results. We think that this is largely because we don't truly understand what we have to do in terms of targeting the inflammatory cascade within the central nervous system. And we should be able to control the detrimental effects afforded by immune upregulation, but at the same time, we need to preserve physiological glial activation. And it is possible that the results seen in our Alzheimer's immunization studies, where we saw a wide, a plethora, if you like, of adverse events, may have been as a result of halting the positive glial activation. Another therapeutic approach that is also coming to the fore is the use of nutraceuticals, curcumin, N3 fatty acids, and others. Although these look promising, thus far in proper human-based studies, we've not seen a positive effect. But again, this modulation between upregulation of inflammation and the immune response to protect the cells is, I think, something that we need to understand further. So we really need to understand the individual contributions of the microglial and astrocytic cells to the neuroinflammatory approach and response in Alzheimer's and other dementias, and recognize that modification of the immune system could provide us with very good therapeutic targets if we can modulate in the right way. I now turn to a very busy slide, forgive me for this, but this is a slide that refers to oncology. And we have seen in the last couple of years a vast surge of immune oncological approaches. We recognize significantly that the immune system is key in fighting disease. And again, this can be applied not only in oncology, but to CNS disorders as well. The concept of immunoediting and neuroprotective autoimmunity appear to converge. And we need to also understand the concept of escape from immunological surveillance in the same way that oncological disorders require or are facilitated by immune escape, so too may neurodegenerative conditions be involved in the same process. So this slide depicts the concept of immunoediting in neurodegeneration. And here you can see that in the first part, you have an absence of clinical symptoms as depicted by the red line. And when you have an insult, toxic accumulation, or injury, you have modulation of the response, but ultimately the body, the CNS, returns to an equilibrium-based baseline. However, when there is immune escape, for whatever reason, in other words, there's upsurgence of disease activity or the body's innate immune response declines, as is common in aging, and here we have the tie-up between aging, which is the main risk factor for dementia and AD, and the immune deficiency response, then once you have that modulation of the immune response, you have the emergence of clinical symptoms. so-called immune escape. So again, a busy slide just showing you a host of targets that are currently being looked at various levels of validation, targeting Alzheimer's disease and other dementias. A lot to be looking out for in the future. What else should we be doing? I think there's a lot to be done in terms of the animal model space. We really need to be developing new animal models that moderate and modulate neuroinflammation in the right way. We also need biomarkers to help facilitate us understanding the immune response within the CNS and the change over time. We need to be able to define pathologies and periods of neuroinflammation in relation to the multiplicity of cell types that contribute to dementia. We also need to be exploiting the effects of mutations, genetic and epigenetic, as well as microbiome factors, and the role that these might be playing in neuroinflammation. And finally, as we were talking just before we started today, we need to be designing real-world observational studies to look at people during the course of their healthy life, before and then as they start to decline, because we know that the duration of the disease is so long. And we also need to start thinking about how we're going to target preventive clinical trials to target the immune response. Coming on to another aspect, and I think we can also learn a lot from other diseases, and this is the epigenetic approach, which is, as you well know, the causal reaction or interaction between genes and their products that bring a given phenotype into being. And here we're looking at inheritable traits that are involved in changes to the chromosome without the changes to the underlying DNA sequence. I think that within CNS, we are relative latecomers to the field of epigenetics, because classically we have only looked at epigenetics in the context of cells that divide. Neuronal cells don't divide, but clearly there is a strong role to play for epigenetics in disorders including Alzheimer's, Parkinson's, Huntington's, ALS, and even epilepsy. And we know that there must be several epigenetics at a molecular level that act, mainly involving two mechanisms: the direct methylation of DNA and modification of histones. So in the same way as we can investigate on a population, individual, cellular, or molecular level in terms of our investigations in Alzheimer's disease, so we can also look at epigenetic alterations in different contexts and at different levels. We can look at bulk changes, we can look at cell type alterations, we can look at locus-specific alterations, and we can come right down to nucleotide-specific alterations. A lot more work needs to be done in this space, and I think that we have a lot of evidence from other studies and other work to support this approach, and a lot more can be done to link epigenetic modification, environmental change, and the onset and progression of dementia. Also, importantly, I think that because we can potentially sample in the brain and the blood, the use of epigenetic markers might offer us a very discrete and targeted way of picking up very early disease, long before patients actually become patients, before they present. And so this is another aspect in which epigenetics may help to serve us well. And neurorestorative strategies also provide another focus for investigation: the use of nerve growth factors and other neurokines which promote neurorestorative and neuroregenerative potential. And finally, my final slide, which has, I think, a lot of thought, a lot for us to think about, is whether we can take a multifaceted approach. Can we learn from oncology, autoimmune disorders, in which we use a multitude of drugs? There's been a lot of talk about this in the dementia and the Alzheimer's space, but, and I say this with a big emphasis, but there are a lot of factors that have to be considered. And these include: how would we run studies? Which patient populations would we use? What stage of the disease would we target? We want to get in as early as possible. How to define people before they become patients? how will we run these studies in real time? How long are they going to take? How do you enter into the study? How do you define the point at which you first can be monitored? How do you define the endpoints? How do we stop the studies? How do we know whether a drug or a multitude of drugs have had an influence or an effect? How do we know when one drug is no longer working to bring in another, as we perhaps do in oncology or other diseases of the immune system? Safety issues in the drugs that we are developing or know is of the utmost importance, because we have to understand that the regulators require that we understand the safety profile of our new drugs, and we also have to understand how they interact with other drugs. And as I mentioned, the regulatory pathway is unprecedented. We will have a lot of work to do with our regulatory colleagues, as well as payers, HTAs, and other people, as well as appealing to the lay public, the members of our society whom we serve, in order to cooperate and work together with us. So I'll stop there, and thank you for your interest, and hand over to the next participant. Thank you.
I'm Clive Ballard from the University of Exeter. I was particularly interested in hearing what Gina was saying about epigenetics, which has been a strong focus of our work in Exeter with John Mill and Katie Lunnan. But today I'm going to talk about things more related to my own background as a clinical trialist. I know I only look about 25, but I've really been doing clinical trials for about 30 years, I think, in this area, initially at King's College London and more recently in Exeter. And what I'm going to talk about really is some reflections about, are we designing trials in the right way, and particularly how do we power trials better, have we got the right outcomes, and particularly in trials of neuropsychiatric symptoms, how do we reduce the placebo response, which makes it very difficult to show positive outcomes. We all know the background, so I won't labour this too much, but a lot of people with dementia worldwide, the majority of whom have Alzheimer's disease, but we shouldn't forget other dementias as well. We haven't had a new licensed drug for about 20 years. As Roger said in the introduction, we've had lots of learnings over that time, but it's been disappointing that we haven't been able to convert that into new and more effective therapies. And to kind of reflect a little bit, actually, that various esteemed leaders in 2012 made pledges that we would cure Alzheimer's disease by 2025. Lots of talk, not so much action, and we're now about halfway through that period, and we don't seem to be any closer to achieving that. So maybe it's a good time to step back a little bit and think why. And perhaps the way we've always been doing things isn't the right way, and maybe from some of these learnings we can do things in a slightly more effective way to lead to better outcomes. So, as we'll all know, and as Gina mentioned, lots of trials of things focusing on amyloid, such as immunotherapy, which have so far been unsuccessful. This is the solanezumab program with a number of large trials which probably showed, with the eye of faith, perhaps a very marginal effect on cognition, but limited statistical benefits and certainly not clinically meaningful benefits. I think one of the learnings from these studies, these are treatments which target amyloid, and in many of the earlier treatment studies which didn't actually measure amyloid in any way using imaging or CSF biomarkers, about 30% of the participants in these trials didn't have amyloid pathology. And in a way, that seems to be an obvious way, and I'll talk a little bit more about enrichment as we go along. But if you're targeting amyloid as a therapeutic target in people who don't have amyloid pathology, that immediately doesn't seem like a very sensible way forward. And that is something that has been now refined in more recent studies, but I think was a very big and very important lesson. So what kind of outcomes can we measure, and how can we improve power in clinical studies? And I think now the regulatory agencies, the EMA and the FDA, are coming round to thinking a little bit more about biomarkers. I think some of the very helpful work has come out of the ADNI Neuroimaging Initiative study in the US. There's a very nice kind of article on ALS Forum that summarizes a number of the papers coming out. But what they've tried to do, looking at sort of annual follow-up in both people with mild cognitive impairment and mild Alzheimer's disease, they've tried to work out, based on the variability and the change over 12 months, how many people would you need to detect a 25% treatment effect, a 25% benefit in treatment compared to usual decline with 80% power and 5% significance. And as you can see that if you look at the ADAS-Cog, which seems to have been the traditional sort of outcome measure in most of the clinical trials that have been conducted, in mild Alzheimer's disease you need over 400 people per treatment arm, not including dropouts, and in mild cognitive impairment it's over 700. So even if you're doing phase 2 trials, if you're trying to power them for those outcomes, you need enormous phase 2 trials, which are going to be very, very expensive and very difficult to run. If you look at sort of some of the other biomarkers, so if you look at neuroimaging biomarkers, for example, the outcomes are much better, probably about 80 patients per arm for FDG PET, probably in the region of 100 to 150 per arm for various MRI outcomes such as medial temporal atrophy. So I think by focusing more on some of these biomarkers, that immediately will give much better power. There is a little bit of a tension because for phase 3 trials, regulators will definitely require more pragmatic outcomes, but a lot of treatments will never ever get to phase 3 trials if you have to do such large and clumsy phase 2 trials with those sort of numbers, and this is perhaps a way of at least testing the initial hypothesis of benefit in a more efficient design that then allows you to move forward to a phase 3 trial if there's evidence of benefit. More recently, we've been looking at this from the Adalaperdine program, and part of the reason for doing that is that although the ADNI work is incredibly useful, this is a cohort study and the inclusion criteria are less rigid than they are for clinical trials. And what you tend to find when you look at clinical trial data is that placebo arms tend to not decline very much. And that's for a number of reasons, but I think one of the reasons is that you have such a selected population. They tend to be a bit younger, they tend to have a lot less medical comorbidity, they tend to be on less other drugs, and as a result of all of that, they tend to decline less. So it might be that you have even less power to measure changes in these different outcomes in a clinical trial population than you do in a cohort study. So we wanted to look at this. And we looked at it using the Lundbeck Adalaperdine phase 3 trial program. So this was a program of 3 large phase 3 clinical trials of Adalaperdine, which actually were all unsuccessful. But what we focused on was the placebo group across those 3 trials. So there were 939 people in the placebo group across the 3 trials. And what we wanted to see was, could you use sensible ways of enriching that population to improve your prediction of decline and therefore potentially improve your power in clinical trial design. So if you look at the overall kind of population, you can see there was sort of a lot of numbers, and then there were 963, and you can see that the numbers that had the different kind of enrichment factors that we were looking at. So we looked at people who were amyloid positive using PET scanning. Unfortunately, only about 15% of this trial cohort had PET scanning, so that was only applicable to a minority of the cohort. We also looked at ApoE4, heterozygotes and homozygotes, and family history of Alzheimer's disease. So if you do that, you can see that actually you significantly improve enrichment by using nearly all of these approaches or by using a combination of these approaches. And in fact, you can achieve 70% power with about 100 patients per treatment arm using ADAS-Cog, which is much improved compared to what you were seeing from the raw data. So just to clarify that a little bit further, if you want to look at 80% power in this population, just in the total phase 3 placebo population using ADAS-Cog, you'd actually need 1,600 patients per treatment arm. If you look at people who are amyloid positive, you'd only need 148. So that's a huge difference. It's a massive enrichment by requiring amyloid to be present. But there were also significant enrichments for ApoE4, particularly homozygotes, but also the combination of ApoE4 with a family history of Alzheimer's disease, and within that group, again, the number per group required was about 230. I think this is a little bit of a trade-off because obviously if you're looking at E4 homozygotes, although it's a very powerful enrichment factor, it's only 3% of the population, so it's going to be a difficult trial to recruit for. On the other hand, if you have access to amyloid PET imaging, that's an extremely good way of enriching the cohort. If you don't, ApoE4 heterozygotes combined with family history will achieve almost as good an enrichment. So I think there are much smarter ways that we can go about enriching trials to actually substantially improve power by using either enrichment at baseline and with the previous slide using kind of biomarker outcomes, and the combination of those two approaches I think can be very powerful. One of the other things that we've been doing in Exeter in collaboration with King's College London is running an online program called Protect. This is a community cohort of people over 50. We have at the moment 25,000 people in the UK doing this. It's an annual cohort study with nested clinical trials, so people complete neuropsychology, various health measures on an annual basis, and we also have genetic data from the participants as well. It's now in Hong Kong as well, and it'll be launched in Norway and the US next year, and hopefully will increase to 100,000 people. Well, what we've started to do as part of this study is to look at other outcome measures, and this is using computerized cognitive assessments. This is the CogTrack system developed by Keith Wesness, which is mainly looking at things like computerized attentional tasks and working memory tasks. And I think what we've been able to demonstrate with this is that you can repeat the measures without learning effects. And part of the problem with traditional cognitive assessments is that there's a lot of variability, but you can't repeat them to reduce that variability because you have learning effects. So with this battery, you can repeat them, well, we demonstrated you could repeat them up to 6 times without learning effects. But the data here are showing 3 repeats, and with 3 repeats you substantially reduce the standard deviation. And actually by doing that, we've demonstrated that actually if you look here, for example, you could get power to an 0.5 effect size. You actually only need 64 patients per treatment arm to show a significant difference on the computerized outcome based on decline over 12 months. So again, we've traditionally used the ADAS-Cog. Regulators are probably going to continue to require us to use that for phase 3 trials, but for phase 2 trials, the ADAS-Cog is so lacking in power, but computerized cognitive assessments actually provide a way of getting meaningful levels of power with achievable levels of participant recruitment. So for the final couple of minutes, I'm just going to switch and talk about trials in neuropsychiatric symptoms, which has been a lot of our own background, focusing on both drug and non-drug trials, treating agitation, psychosis in people with Alzheimer's disease and other dementias. But the real big thorn in the side of these trials has been the huge placebo response rate. I mean, this is one of the trials of quetiapine, but you can see that if you look at the placebo treatment group, you can see how big the differences are. For NPI psychosis, for example, a 2.5-point improvement over the 12 weeks of the trial in placebo. Across all 18 trials of antipsychotics for treating neuropsychiatric symptoms, across all of those trials, the meta-analysis suggests that if you define a placebo responder as a 30% improvement, about 55% of people actually respond to active drug, but 45% of people respond to placebo. So again, you can see the problem. If you've got 45% placebo responders in those studies, it's going to make it very, very difficult to achieve a significant benefit over and above that. I think there's a lesson there in itself about what's driving those non-specific benefits and kind of the values of good clinical practice as part of doing that. But I think for clinical trials, we need to find a better way forward to reducing that placebo response. So we've kind of done a number of things to try and achieve that, and this has been done through several programs, but what I'm going to talk to you about here is the pimavanserin program that we were involved with Arcadia, looking at pimavanserin. And as part of that program, we had a number of discussions with the FDA to look at how to kind of improve the design. So partly it was kind of increasing the baseline severity, because a lot of earlier trials had a very low threshold of symptoms, partly using a small number of well-trained raters to reduce the variability, and using the Medavante method that each time point was assessed by a different rater, streamlining some of the outcome measures, but perhaps most importantly of all, using something we call brief psychosocial treatment during screening. So this was a psychological therapy to enhance 10 to 15 minutes a day of the caregiver spending with the person with dementia during the 3 or 4 weeks of the running period. And people who improved below the inclusion threshold over this time were then not included. So what that basically meant was that about 20% of people were not included in the study because they improved during the non-drug therapy run-in. But I think what that then achieved was significant benefits in terms of the trial outcomes. So this was the basic design, and as you can see there, the run-in with a brief psychosocial treatment and then a fairly standard sort of design. So what we can see, if you look at the 30% improvement, which is the sort of traditional level of defined as responder, we can see that there's a 37% placebo response in these trials compared to about a 45% response in most of the trials. So it reduces the placebo response by about 8%. But that's enough to then create actually a meaningful difference between the treatment arms. So that's quite an important impact. We've also done this in trials of Parkinson's psychosis, and again you can see a much more modest treatment response when we've used those approaches. And particularly in that latter trial, when you look at the subgroup of people with Parkinson's dementia and psychosis, you can see that there was hardly any placebo response in that group. So we believe that that kind of trial design, and particularly the bit with the psychological therapy as the run-in, really did actually have quite a big impact in reducing placebo rates. I've waffled on too much, so I will shut up at that point. Thank you.
We're very excited to talk about the challenges in Alzheimer's disease when it comes to trial design. Gina and Clive, they basically covered the whole picture, but I'll try and fill in the gaps, especially when it comes to trial design. So now we know, this has been known for many years now that, complex neurological disorders like Alzheimer's, Parkinson's, multiple sclerosis have been plagued by several complexities when it comes to trial design. Some of those are slow recruitment, lack of especially sensitive over time kind of endpoints. These are mostly instruments for assessing cognition, function, and behavior. These are widely used. Biomarkers are gaining in popularity, and as Clive and Gina both mentioned, that there should be clinical trials where biomarkers are part of the investigation, and perhaps enrichment is probably one of the crucial ways to find out what's working for who. Sort of questions. There's a lack of consensus or guidance from FDA or EMA on what is a minimally relevant effect size. Most of the effect sizes seen in literature are pretty small for powering clinical trials with adequate power. Or even there is lack of consensus as to how long a trial should go on for, how long the follow-up per patient should be, for example. Disease progression is highly unpredictable, thus, time to event kind of endpoints, for example, from one stage to the next stage, could be a problematic endpoint. Again, problematic in the sense of what is the duration of the clinical trial and what is the sample size. So there are two aspects that I'll focus on. One is looking at, endpoints for these kind of trials, especially in Alzheimer's, and also looking at, where can we be more flexible with trial designs. So in terms of the primary endpoint, now for clinical trials, we all know that we have to put down pre-specify a primary endpoint, and there could be lots of secondary endpoints. The problem here is, these instruments used to study Alzheimer's, they might capture different dimensions of cognition, behavior, function. And the point is, and these instruments might be sensitive for a particular population but not so sensitive for another population, or they might all be sensitive but the signals might be very weak. And so there's an interest in asking the question, can we combine these small signals and make it a bigger signal? That's easy to see, that's easy to investigate. So it's a very practical question. Now, can we also look at endpoints like time to disease progression, or, in late stage patients, something as, practical as, time to, family giving up, taking care of the patient. They have to be transferred to a home. So the question is, composite endpoints that aim to combine small signals from different endpoints, and these endpoints could be time to event endpoints, continuous endpoints, scores, ordinal responses. Can we combine these to come up with a stronger signal? There are two examples, and these are, you see, this is O'Brien's method from 1984 and Finkelstein-Schoenfeld statistic from 1999. So these things have been around and people have thought about these things. So the O'Brien's, what it does, it's an average rank sum test. It's a non-parametric test. Now, non-parametric tests have, their advantages, but also disadvantages. So does every kind of statistics, right? So what it does is it ranks patient according to each endpoint. So I might get a rank of 1 on a particular endpoint because I did particularly well on that endpoint, but on another endpoint I didn't do that well. So, I take an average rank score, and then I look at what are the rank scores in the treatment group versus what are the rank scores in the placebo group. Very simple to understand. The Finkelstein-Schoenfeld approach brings in another very interesting question is, can we define the priority in terms of the endpoints? Is there an endpoint that is most interesting or most relevant? What is the next one? So you pre-specify a hierarchy of endpoints according to clinical priority, and then compare each treatment arm patient to a control arm patient. So I take 2 patients, one from the treatment arm, one from the control arm, and then I compare them on the first endpoint. If I can choose a winner, then I'm done with that comparison. I give +1 to the winner and -1 to the loser. If I can't, if there's a tie, so for example, if there is a time to event sort of a question, let's say time to disease progression, and they both haven't progressed, so these times are censored, right? So I cannot break the tie. Then I go to the next endpoint. If there's still a tie. So these kind of questions are very relevant for things like time to event data, but also score data. So score data, somebody might decrease on their ADAS-Cog by 2 points, and somebody might decrease by 3 points. Is that clinically relevant, right? Perhaps not. Perhaps a comparison between 2 and 4 is more relevant. So we can bring in these kind of clinical thinking in defining these comparisons. Once we have compared all the subjects, all the treatment patients with the control patients, we take the sum of the scores obtained in the treatment group, and that gives us the statistics of interest. That statistic tests the hypothesis that if you randomly pick up 2 patients, one from the treatment group, one from the control arm, what is the chance that the treatment arm patient will be showing better results, right? It's a very simple probability that this score test estimates or tests. So that's about endpoint. Now let's talk about some aspects of trial design. Now this is from the ADDF Foundation Harvard Phillips report in 2017, and one of the points he wants to put out is we need smarter clinical trial designs for studying Alzheimer's. There's an initiative, a recent initiative by the FDA that announced the Complex Design Initiative for late-stage drug development for complex diseases. And this complex innovative designs also include Bayesian designs. And Bayesian designs, you know, I've used Bayesian designs in a lot of other diseases, but I think, especially in exploratory studies and early phase studies, but I think there's a case for Bayesian designs for studying Alzheimer's, even for late phase development. And this initiative by the FDA allows for late phase development using such innovative designs. So a little bit about Bayesian designs. Now, we all know in frequentist designs, what we do is we assume certain things about the endpoints, what is the effect size going to be, what is the variability, and we do some power calculations. And Clive showed you how, if you account for placebo effect, or if you can look at a particular population where the placebo effect is lower, then you gain in power. So you do these kind of tasks before you start a clinical trial, and then the clinical trial starts, and then you look at the result, after a few years. You might have interim looks, but there is hardly any possibility to tweak your clinical trial at that point. There are some possibilities that you can use, for example, sample size re-estimation or population enrichment, but there is nothing that allows for sequential development. Now, what I mean by sequential development here is not looking at, let's say, after 100 patients are done in the trial, I take an interim look. Perhaps we could take an interim look after every 20 patients, right? And then, slow but steady development, very careful development, right? So what a Bayesian trial does, it starts with a prior belief. It's basically a distribution. What is the distribution of my treatment effect, right? That's your prior belief. And if you're starting from scratch, then you don't have any prior belief, right? And then as you go through, you modify or update your prior belief. Basically, it's called the posterior update. And then you look at your posterior update at pre-specified intervals via multiple interim analysis. At each interim analysis, you calculate, there are lots of different calculations you can do, but one of the popular ones is this posterior predictive probability of success. So you look at each, so after 10 patients per arm, so 20 patients, you look at what is your PPP, your posterior predictive probability. If it is good, you continue. If it is even better, you still continue. If it is not so good, you can stop quite early, right? So by the time you're at your 4th or 5th interim, your chances of success are pretty good, right? And that also, sort of goes in line with how investors think about, investing in clinical trials. And the rule, there are many ways to come up with stopping rules. If at a certain interim the PPP exceeds a pre-specified high level, let's say my posterior predictive probability of success is more than 90%, then I stop recruitment, and then I go to my final analysis, right? And that could be a design. Also, you could look at this PPP, and if the PPP is very small, let's say less than 20%, then you can stop for futility. Bayesian design's good things is, Clive and Gina talked about, other aspects. One of them was biomarker, how biomarker should be, introduced within this clinical trials in the area of Alzheimer's. And the Bayesian designs would provide a framework for biomarker-guided adaptations. So as you go through, if you are seeing that, look, for a particular biomarker-positive population, my posterior predictive probability is higher than the negative, then you adapt according to strategy, so enrichment strategies. Seamless phase 2B designs can be incorporated, so after your 2B, you have some data and you build your prior belief, and then based on that prior belief, you go and start your phase 3 trial. What happens in Bayesian designs differently to frequentist design is that a strong sample size or trial duration does not have to be pre-specified. You can, of course, pre-specify what's a maximum that, that is expected. However, statistical validity of Bayesian designs, like any other designs, have to be looked at in terms of operating characteristics. And what is most important is these designs must be shared with the regulatory agency. I already talked about the CDI, the Complex Trial Initiative. The number of timing of interim analyses can be determined using simulations, another important task. Overall, basically, like any other adaptive designs, rigorous upfront planning will be typically needed. And this is probably much more difficult part compared to classical designs. Thank you, everybody.
We're almost out of time, and I was trying not to do that. Has anyone got any questions? I know we're running out close to the end of the session, but I also know you can email session. I don't know that. Okay. The microphone's coming. Hang on.
Thank you very much. I don't know if I am going to make some question, but first I would like to thank you for preparing this interesting meeting, trying to be thought-provoking, breaking all things. I am biochemist and molecular biologist, but I think that the time of biochemistry and molecular biology needs to be down. It's now the time of more interdisciplinarity, more going into psychology and all these sort of things. And you have been presented here these new ways to approach that. You do think that it is necessary to change the FDA and European Medical Agency uses in order to change the views about the trials? Because if not, we are going to do wrong things, to lose a lot of money, to create a lot of expectations that are not fulfilled, and that is a pity. Thank you very much.
Anyone want to comment on that? Any other questions? Or I mean, thank you for that. It's what we were trying to achieve. I mean, you know, we have this language of failure, and actually what we might have is you know, we need to do things differently. Carlos.
The very reason that the last comment on my last slide mentioned the regulatory pathway is exactly that. If we keep doing things in the same way, if the barriers, the hurdles, I mean, they're there for the right reasons, but if they remain constant, unchanging, then I don't believe we'll actually get anywhere. If we do our clinical development, if we do our clinical trials in the same way that we've been doing for the last 20, 30 years, then I fear that the next 20, 30 years will be the same. So I think everybody has to approach this in a very different way, and we need to work collaboratively, not us against them.
Learning from other fields as well. And I think, you know, Gina mentioned oncology, but I mean, there's been a lot of development around enrichment approaches, trial design, and I think it's time that we, you know, use that information a bit more effectively.
I was just going to add, saying that, look, means FDA, people at FDA and EMA, they are constantly thinking about the same questions, you know, as we are, right? And the complex trial initiative is one example, and I think, you know, people should take advantage and learn, you know, how to use these different pathways, you know.
So when you design a drug and you start to push the development, you have a clock ticking, a patent clock ticking. So for this, when you go designing trials to look at prodromal disease and are thinking of trials that have a really long duration, should there be a patent life extension for these type of drugs? Should there be a movement that tries to extend the patent life?
I think that would be helpful. I don't know whether it's going to happen. You know, as we have been to move earlier and earlier in the disease pathway, and we're looking at working with essentially healthy people who are just starting to decline, then the duration of a study will have to be long, especially if we're going to be looking at real-world behavior. At the present time, patent life is a big issue, cost expense is a big issue, and senior management in most companies don't want to hear that they're going to have to invest in a study that's going to last 10 to 15 years. That's just not going to happen. So there are lots of factors, I think, that play a part.
And I think it's also an important reason to think about enriched phase 2 designs, which are more biomarker driven, so that the phase 2 trials can be done a bit more quickly and cost effectively.
If there is no other questions on the audience, I will go for one, or maybe for a few ones. So I think that one of the interesting points today was Gina's one about the importance of inflammation on the onset and the progression of the disease. And we have seen a number of interesting papers being published, even connecting the immunocheckpoints with some of the responses on the microglia activation. So what will we be expecting from anti-inflammatory drug, and to what extent that could open some ways to get peripheral biomarkers that could be surrogative of at least action of the drug, if not from clinical benefits. So on your view, how this could evolve in the future?
Could I just add, as well as the peripheral biomarkers, could I just add the question about whether some of the PET markers for microglial activation and neuroinflammation could be of value?
Well, yes, I think that they can be. I mean, we are looking at central markers of inflammation, astrocytic or microglial activation, and by the same point, if these are transmigratory mechanisms, then we should be able to look at peripheral-based or fluid-based biomarkers, which, as you know, in Alzheimer's disease are not yet available. Really, I think the Holy Grail would be a simple, easy, blood-based biomarker. We definitely aren't there yet, but it is much easier, as you well know, to access peripheral circulation than it is the central. And if we have the two speaking to each other or transmigrating, there may be a way in which to do that. Looking at other neuroinflammatory disorders, in multiple sclerosis, for example, where we understand the inflammation, we don't understand the degenerative component, we can do that to some extent. How this then ties into the progression, the cognitive progression, remains yet to be seen. And of course, the temporal framework is something I think that we don't understand at all, not at this point. So there's a lot of work to be done, but in some ways it may be more tractable than trying to continually look at centrally based changes that we're not quite sure how they impact and reflect on the disease per se. So the extensive failure, if you like, of the amyloid approach at the moment makes many people wonder as to, is it the target, is it the time, is it the way in which the target is manipulated? We still don't know. I think if we take an inflammation-based approach, the same questions are likely to raise their heads, but we again may be able to look at other disease processes where we understand that a little bit better. I mean, it's a lot of questions, a lot of hypotheses, But I do believe this is something we should be looking at, and the field is looking at it, perhaps now with or heightened vigor than when everybody was still jumping onto the amyloid-only bandwagon.
Okay, the Horizon came here to push boundaries, and we've succeeded on pushing the boundaries of the session as well, because we're 5 minutes over. So I think we'll have to stop there. And the speakers are around over coffee if you want to ask any more questions. I think all I need to do now is thank them for their presentations and you for your attention. Thank you.